Hey, Mrs. Lemke here, and I'm gladly and excitedly here to talk to you today about something called the fundamental theorem of calculus. It's very, very cool, you guys. I can't even understate it. It gives me goosebumps even to this day, even after knowing about it for decades. But you might wonder about that word fundamental. And clearly the word fundamental is indeed fun, but what in the world is up with this word fundamental? Well, it turns out that mathematicians love the word fundamental. They love it so much that if you do a quick little Google search, you get like a quite the list of things that are fundamental theorems within different areas of mathematics. And it's important to know that it's not necessarily the most commonly used theorem, although this particular one we're talking about today is indeed used quite a lot in calculus. So the fundamental theorem of calculus actually does get used quite a lot. But it is the thing that is the most pivotal idea within an area of study. So if we're thinking about arithmetic, one of the things that is really, really key in the area of arithmetic is the idea that numbers are composed of primes or are themselves prime. So when I look at integers, at natural numbers, I can either break them down into primes or they are themselves a prime number. And that is just really, really key and important within the structure of our number system. And in fact, if you're really interested in primes, I would encourage you to at some point take a course in number theory. That's what it's called, number theory. And I took two of these classes when I was in college, and one of them was when I was on my study abroad program in Budapest, and the other one was when I returned to the States and did an independent study, but with my husband. So my husband and I, not married at the time, clearly, we were in college, did an independent study with a professor in analytic number theory. And it's such a strange experience because you're really talking about basic math, prime, not prime, things like this. But at the same time doing really abstract math, and we were doing some computer programming as well. It was kind of a surreal experience. And, clearly romantic because we've been married for quite a long time after that, And then, so be careful who you sign up for number theory with, Anyway, what is the fundamental theorem of algebra? Well, a key idea of algebra has to do with solving equations. And in particular, in high school algebra, one of the things we work on solving quite a lot are polynomial equations. So this fundamental theorem of algebra says, hey, when you're looking at a polynomial, y equals blah, 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 that has x in it, x to different powers, if you're looking at that, you're going to find at least one root. And when we say root here, our domain that we're thinking about are the complex numbers. So the roots might involve I, they might not, but there is at least one such root. And these existence theorems are very important in math because we don't want to be looking for solutions that don't even exist. So it's important to know that they exist. So that's just a little bit of backup and a little bit of amusement at how funny it is that there's so many of these fundamental theorems. I find that hilarious. It's like we can't think of a new name, but I mean, it is what it is, right? If it's the most important idea, it should be called the fundamental theorem. So what is the fundamental theorem? Well, I'm going to go back to a couple of things that you've heard about in the lessons that Mr. Covey has recorded and that we've talked about in class lately, because there's just been a couple of strands of development in the math that you've done in class lately. And today is the day when we kind of weave them together. In my head, I really picture making a braid, right? You have this strand that's going on with area under a curve, and you have this strand that's going on with antiderivatives. That's kind of interesting, and we're going to try to weave those together today. So a really nice little question. Okay, suppose that you are starting 10 miles away from your house and you're going 40 miles per hour directly. Oh, you're starting. Oh, wait, my words don't make sense here. Hold on. Okay, my words make sense. I just didn't make sense. Okay, so if you're starting 10 miles away from your house, so you're not at your house to begin with, but you're 10 miles away from your house, and then you're moving even further away from your house. So you're going 40 miles per hour further away from your house. How far away from your house are you after an hour? Well, you started out 10 miles away. You spent an hour traveling. The hour that you spent traveling is spent going 40 miles an hour. So it seems to me that at this point you'd be 50 miles away. Similarly, if you go another hour, you're going to add on another 40 miles. That would be 90. So the pattern or the idea that we're using is, hey, I'm starting 10 miles away, and then I get another 40 for every 1 hour, T hours that passes, okay? So if we think of that as our position function, I want to think now about my velocity. Oh, my velocity equation was 40, right? That's what this was about up here. And so if I were to picture this, right, here's my velocity function, a constant function of 40, then I know, like between hour 1 and hour 2, for example, I'd have this rectangle, and that rectangle had an area of 40, which is why I was adding 40. I also know, though, that position is the antiderivative of velocity. So it seems like here, this is like anti-differentiating with a constant of c, or like a constant, my constant c is 10, but I also have this idea that there's something here about the area. So it seems like area is related to antiderivatives somehow. Let's look at another example. So now this is slightly more example. So suppose the velocity of a car is 2t plus 1. So it's not a constant velocity, but it is something that can be modeled mathematically. So if the car starts at 20 feet, like 20 feet from some given place that we're calling 0, so like your home is 0 or something, right? Like you define that how you want. Then what is the equation for the position of the car? Well, I know that if I have velocity, right, position is the antiderivative of velocity. So position has to be, I'll just anti-differentiate this, use some power rule, and I know that I'd have a constant right here. But I also know that it said the car starts at 20 feet. So if it says start, that would mean time is 0. So put in a 0, and my constant here would have to be 20 in order to make that work out, right? That's like my initial value. So what is the position of the car at time equals 10? Well, that's not too hard math. So I would be at 130. So what is the change in position from time equals 0 to time equals 10? Well, position at 10 minus position at 0 is what they're just asking me. My position at 10 was 130. My starting position was 20. And so that would give me 110. And now let's turn our attention to this diagram. And I've added a little bit to this very, very out of scale diagram where the dotted line that was drawn in was representing the velocity function. So if I were to put in velocity at time equals 10, right, to try to determine that over here, I would get put in 10, output of 21. So this point on the velocity function is 10, 21. This point would be 0, 1, because I had a starting, like if I put in 0 for t, I'd get 1 for v. So my velocity function is a linear function that goes from 0, 1 to 10, 21. And if you look at this and think about the area under that curve or that line, this part is a 1 by 10 rectangle for an area of 10. And now you'll see what I mean about the out of scale. This height is 21, but this part of the rectangle had a height of 1. So this triangle, this part represents 20. I know that's hilarious. And this part is 10. So 20 by 10 and cut in half, right? This would be my rectangle that's 20 by 10, and then cut in half, this area is 100. I know, totally out of scale, just roll with it. Okay, so this area is 110, but this difference gave me 110. So it looks like area is related to the difference in the antiderivative values. So this is what we just figured out, right? S of 10, position at 10 minus position at 0 was 130 minus 20, which was 110 feet. But some other things that we know, kind of makes me think this. So this represents the area under the velocity curve. And I got the same answer that I did up here. But how is velocity related to position again? So it's like the antiderivative of this is here. And these numbers are here. Okay? There's something else in your packet, but I'm going to skim past that. And let's take a look at the wonderful fundamental theorem of calculus. Okay, so what we just saw in that last example was it. It was a specific example, right, rather than the general theorem, but it says you take a function, you find its antiderivative, you put the bounds from that integral, from that definite integral in and subtract, and that's going to tell you the area under the curve. What? So you're telling me that the antiderivative that we've been doodling around with and area under a curve are actually related? See, this is what's stunning though, okay? So just take a minute, don't worry about the notes, but just listen, okay? Calculus started with the question of rate of change. Rate of change led us to thinking about slope, led us to thinking about a secant line, pushing those points together to become a tangent line, finding the slope of that tangent line. So the question of steepness led to something called the derivative. And for some crazy reason, it turns out that this whole other question of area of weird shapes has exactly the opposite mathematics behind it. And that's what's stunning. I just imagine Leibniz and Newton working on this and just dropping their pens, spilling the whole ink bottle because they're just so stunned at what came about, because these two totally different questions, steepness of a curve, area of a weird space, they're actually related to each other by opposite mathematics. That's crazy. All right, so that's just a moment of appreciation. Let's look at the slide. So the fundamental theorem of calculus gives us a relation, as I was saying, between antiderivatives and area under a curve. This is the notation that we use right here. So this you've seen, we've used that set of symbols to mean the area under function f from a location A to a location B, so the area of this space. We've talked about that, okay? The way that we write this is to say, hey, let's find the antiderivative. So big F is a symbol that means the antiderivative of lowercase f. And then we keep our bounds. So this step with the red arrow, all that would have happened in that step is writing out the equation of the antiderivative, but you haven't done anything with the bounds yet, but you can't lose track of them, okay? If you're going to put the very powerful equal sign here, you have to have things that actually are equal. So if you dropped the bounds, you'd have dropped part of the question, okay? So we write a vertical line with the bounds still there to keep track of them, and then we evaluate that antiderivative at those two locations and subtract, okay? So that's the key. We will also see having the independent variable up here as part of the fundamental theorem, but I'm going to save conversation about that for a future video, okay? So now we have a bunch of problems, okay? And so for the first few, I'm going to lead you through, and the next few, I'm going to ask you to pause the video and see how you do, okay? the mechanics of this are actually not that bad. You've actually done all of the work of it before. It's just putting things together. So now when I want to find the area under the curve, I don't have to do Riemann sums. I don't have to do a limit summation, although that is super fun. I now can use this idea that I know that antiderivatives give me area. So I'm going to take this expression. I want to find the area of this yellow region, and I'm just going to say, hey, let's anti-differentiate that. 1/3 x to the third. I want to keep track of those bounds of my definite integral, so I write a vertical line and I put my bounds on it. I have seen some people do like a little bracket thing. I don't really love that just because I feel like it does get confused with parentheses, and this vertical line is unique to evaluate at, right? That's kind of what that means in calculus life. Then I put in the upper bound and then the lower bound. Upper and lower meaning this was the upper number, this was the lower number. So even if they were flip-flopped around, this is still like the upper bound and this is the lower bound. Usually if we have it in the order that doesn't make as much sense, right, the bigger number is in the lower area, we will use that property of integrals to flip the bounds and put a negative sign in front to make that all make more sense, okay? And then here, I just evaluate that math and I get 7/3. Oh my goodness. See, I'm writing like more and more like Covey. Covey, you're rubbing off on me. That was sort of a slam. Okay, so you might wonder at this point, what happened to the plus C, right? Because all the time we've been all about adding C, adding C. What's the big deal with the plus C, right? So understand that this kind of just works out in the sense that you're finding a specific area, you're not anti-differentiating, and you can sort of think of it like there's a C in here, and there's an arbitrary constant in there, but the subtraction makes it go away. So that's not precisely mathematically a great explanation, but bear in mind what you're actually doing. You're finding area. Area is not going to be like something plus a constant, you know? So think about the kind of question you have. And then also bear in mind, there's a great thing you can do on your calculator. So I wanted to make sure that you knew that this is a time when you can use fn_int, right? So, or you can use this tool on your calculator. Like if you're in the graphing part, you can say, I would like to find the area. So I'm just going to throw that out there, and we'll spend some more time in class if you haven't sorted out how to use that fn_int tool. All right, here's our next example. It says find the area between the x-axis and the curve of y equals cosine from 0 to pi over 2. So we are going to set this up, lower bound, upper bound. My function is the cosine function, and I would like to find its area. So I'm going to anti-differentiate. I'm going to put my bounds over here to keep track of them. I'm going to substitute in based on the fundamental theorem. And then that would be 1 minus 0 or 1. Now you see, this is also like a really cool math fact, right? We have these trig functions. The trig functions come from knowing like SOHCAHTOA, right? And then you build that into unit circle. And in the unit circle, you say, okay, I'm going to take angles versus, one of the coordinates, and I'm going to make a graph out of that. And so here's my, cosine curve. And then this area ends up being an actual integer, a whole number. Like that's stunning. It came out as 1? Really? Wow. Just saying. That's amazing. Okay. There are several more examples that I'd like you to try. I think questions 3 through 8. Question 8, you do need to be a little clever, / you could try to use fn_int on your calculator, okay? So I'd like you to try all of those, and then the rest of the video is just going to be the answers to them, and I think maybe a little bit of calculator help, okay? So go try, come back. Okay, So question 3 is just a polynomial. So you anti-differentiate. You can see that the author of this answer key, like the bracket thing that I mentioned, I don't love, but what else? And then you plug in the 3, plug in the 1, subtract, you should get 38. For example 2, or example 4, the second one you did by yourself, don't be rigged out by the change in variable, right? So this is U instead of X. It's still the same math. It could have been heart, it could have been Bugs Bunny, it doesn't matter. The math works the same. So you anti-differentiate, and then this minus here would have made this become a plus when you anti-differentiated. Plug in your bounds and subtract. You get -2. So negative area, think about what that means. What does that mean? All right, example 5. You do need to do a little bit of algebra here in order to anti-differentiate. So please understand that you can't just go at that and take an antiderivative of each part. That is not going to work out, because I need to make sure that if I were to take the derivative of this, I should get what was my original problem. And if I were to just anti-differentiate each part of this, like that, and say, okay, that's t to the 1/2. If I just anti-differentiated each part of this, the derivative of this is not the original problem, because of product rule. Okay, so please don't make that silly mistake. Okay, you do need to have something to which your antiderivative rules apply. So we needed to tweak that a little with some algebra, and then this is the decimal. This is not the decimal. This is the exact value. So if you have a decimal, type in 16 times √2/15 on that calculator that you had to get your decimal, and see if we match. For question 6. We need to remember our rules for trig functions. So the derivative of cotangent would be negative cosecant squared. So going this way is exactly the opposite of that. And then evaluate by plugging in your bounds and subtracting. Watch your pluses and minuses here, okay? Because you're subtracting all of this evaluated at pi/4. And for example 7, I think everything in this question we've already discussed. Watch your signs, right in here. But other than that, I don't think that question's particularly challenging. But this one is. So do we have an antiderivative rule for absolute value? No, we don't. Okay, this is an issue where going from 0 to 3, I actually should have this colored in up to here. Trying to find that area would be easy if I think about this just as geometry, right? I might have to say, all right, I want to break this into 2 little triangles and find the area. Find the area of the first bit going from 0 to 1.5, and then find the area of the other part going from 1.5 to 3. And I wouldn't be using absolute value anymore. I would find the equation of this line, and I'd find the equation of that line. And so that's what I would do. I'd set it up like 0 to 3/2. This would be the opposite line, like this is the part that's reflected over. And then I would add to that the area from 1.5 to 3. And this is just this typical without the absolute value. That's the equation of this line. Now I hope that you're not thrown by finding the equation of lines, right? This is going through at 3, having a negative slope. This is going through at -3 and having a positive slope. Okay, so that's all that happened there, would be splitting it up. But this is actually a decent question to talk about those calculator functions, okay? I said I was going to save it for class, and now I'm thinking maybe we shouldn't do that. So right here, I put in the function that we're talking about, absolute value of 2x minus 3. The absolute value is found in math, over the number, and pick absolute value. All right, then in the math menu also, there's this thing called function numerical integration, or FNInt, okay? I'm going to choose item number 9, and then you can see that I have the ability to just type in the integral that's on my page. Since I already put my function in as y1, I'm going to go to the variables key, over to y variables, and pick up the symbol for y1. That was just because I didn't want to have to type it again. You equally well could have just typed it in right there. Okay, and then that tells you the area, which is pretty nice. Okay, if you have an older calculator, like one of my calculators is an older one, when I type that, I just get brackets, like an open bracket. And so if that's the case for you, the syntax would be put in the equation, so like y1, and then a comma, and then x to signal that is dx that you're looking at, and then you put in your lower bound, and then your upper bound, and close your parentheses. So if you have an older calculator, there you go, okay? All right, so this is just the summary. This is the thing that we hopefully learned today, okay? And I wanted to make sure that we had actually pointed out the conditions of the theorem, because as I've told some of you, AP loves to make sure that you know the conditions. So in order for this to be a working theorem, our function that we are integrating has to be continuous between A and B. And if that's true, so it's a continuity condition. If that's true, then it is true that the area between A and B under that function can be found in this way. Okay, antiderivative, plug in the bounds, and subtract. Thanks so much.